We're going to start 6-2. We'll get through A and B and start C. This is a little bit easier than 6.1. Like, we're going to take a step back from the systems. So we're not going to do augmented matrices, just regular matrices, and talk about some operations, like adding, subtracting, and then multiplying. So the first few operations that we do, addition, subtraction, multiplying by a scalar, those are all pretty basic. The multiplying matrices will look a little bit different, but it's still not too difficult, but it's just not as straightforward as the others. Okay, so we will do A, B, and part of C today. Okay, so this looks a lot more confusing than it is. This is something we've already talked about. This just talks about how to name the positions of the entries in the matrix. So if this general matrix is A, that's a capital A, and then the entries are these lowercase a's. So for example, this entry here, that's A23, that means row 2, column 3. Okay, that's A23, that's where that comes from. And that can go on and on. So the last one we say, okay, just row M and column N. Okay, so A-N, M-N there. Okay. The size of a matrix, so we've talked about that as well, but it's also called its order. So if they ask you to find the order of a matrix, that's just they're asking for you to find the size. And it's written as row by column. So row by column. Okay, so for 10 and 12, we're going to first state the order of each matrix. So that means state the size. And then name the entries and positions A12 and A23 if they exist. And then we'll name the position of the entry 5 there. Okay, so we first want to find the size. And we do row by column. Okay, so how many rows, and number 10, how many rows does this matrix have? 3. And how many columns? 2. Okay, 3 by 2. Okay. Then I want to find the entry and position A12. So that's row 1, column 2. So that would be what? Row 1, column 2. Where do those cross? .4. Okay. Row 1, column 2. They cross, they intersect at 0.4. Okay. A23 would be row 2 and column. A23 would be row 2, column 3. I don't have a column 3, right? So that's why it says if they exist. It does not exist. Okay. And then it wants to know, okay, what is the position of 5? So here's 5. So that's row 2, so 2, and column 2. So A2, 2. All right, do the same thing for number 12. So I'll give you a minute for you to do this one. So, Susan, what's the order? What's the size of this matrix? Okay, good. So 3 by 4. Good. Jacob, what is the entry for A12? Okay, so row 1, column 2 is 55. Good. And Corey, what about A23? Okay, so then 5 is in the position A23. Good. Questions about that? Okay. So we're going to talk about equality matrices here. So it says, determine if the following statements are true, false, or conditional. If false, explain why. If conditional, find the values of the variables that will make the statement true. So conditional just means if there's variables. Matrices are equal if all corresponding parts are equal. So if all corresponding entries are equal and they're the same size. So basically if they're identical, then you could say they're equal. So just like real numbers, 2 is equal to 2, has to be the same. Okay, so this one is conditional because I have variables. So it means conditional because it will be true, it'll be equal based on the condition that this entry, 2p plus 1, equals this entry, 7. That's why it's called conditional. So let's find p. This doesn't have a, b, or c, so it just has p, q, and r. So 2p plus 1 equals 7. So 2p equals 6. P would be 3. I see p another place too. So 3p here, which one would that correspond to? 9. So if I did 9 equals 3p, would I get p equals 3? Yeah, so it doesn't matter which one you use. All right, so Q. So let me start on this matrix. So I see Q here. So 2 minus Q. And I want to set that equal to what on the other matrix? 9. Okay. also could have done q plus 5 equals negative 2. That would have been fine to do as well. So negative q equals 7. So q equals negative 7. All right, so then r, go ahead and find r. No, they should be the same. They should be the same. The only reason why you might want to check is just that you calculated it correctly. Hannah Singer, what equation did you set up for to find r? Okay, good. So negative 2r equals negative 8. We also could have done 12 equals 3r. In either case, you get r equals 4. Questions about that? So the problems before 16, the ones that you would say are true or false, wouldn't have variables. They are just all numbers, and you just check. If they're the same, it's true. If they had different numbers and certain positions, it'd be false. So that's what that first statement means. Okay. Questions about that? All right, let's look at addition and subtraction. So the addition properties of real numbers hold true with the addition properties of matrices. So it's commutative. Like with real numbers, 2 plus 3 is the same thing as 3 plus 2. The order doesn't matter. It can be associative. So you could add the first two together and then the third one. Or you could add the second and third one together and then the first one and get the same thing. You have an additive identity. So with real numbers, the additive identity is 0. It's whatever you can add or subtract to itself to get the same thing. So 5 plus 0 is 5. So with matrices, you have an additive identity. We call it Z. And it's just a matrix full of zeros. So, and it's whatever size you need based on what size A is. So it's just a matrix full of zeros. Notice that it says that they are all M by N matrices. So they're all the same size. So to add or subtract matrices, they have to be the exact same size. That doesn't mean they have to be the same number of rows and columns. Like they don't have to be square matrices where they're all 2 by 2s or 3 by 3s. They just have to be the same. So if the first one is a 2 by 3, then the second one needs to be a 2 by 3. Then, we also can talk about additive inverse, so the opposite of A. It's like with real numbers, you have 2 and negative 2. Those are additive inverses. Okay, so let's just practice adding. we'll be able to scroll down so we can see G. Everybody okay if I scroll down? So I want to do E plus G. So check the size. The sizes have to be the same. So what's the size of E? 3 by 3. What about G? 3 by 3. Okay. So I'm going to get another 3 by 3 matrix. And to add or subtract, I just add corresponding entries. So I'm going to add 1 plus negative 1. Oh, yeah. Okay. So 1 plus negative 1. So the top left with the top left. Okay. And then negative 2 plus 2. You do not have to show all of this work, but I just want to show it now so you know where we're getting these numbers. 0 plus 0. 0 plus 0. Negative 1 plus 1. 2 plus negative 2. 4 plus negative 4. 3 plus negative 3. And negative 6 plus 6. Okay, so add those together, and I end up getting all zeros, which is Z. Now you don't have to write the equals Z, I won't expect that of you, but you do need to understand, like, if it tells you to do, like, matrix A plus Z, that Z would just be a matrix full of zeros. Same size as whatever the first one is that you're using. Okay? Questions about that? All right, let's look at A plus D. So what size is matrix A? 2 by 2. What about D? Okay, are those the same size? No. So this is not possible. Is that what you would like to say? Yep. Oh. Okay. If you're subtracting, they also have to be the same size, and you just subtract. So instead of adding all the corresponding entries, you subtract. All right, we're going to start multiplication, but the first multiplication we'll look at is just the scalar multiplication.
So we would get numbers in there.
Yeah, yeah. It would be what?
No, last one.
subtraction, all that is like distributive property. Okay, so if you're going to do k times a, then you just multiply k, whatever that number is, by all the entries in a. So, like I said, it's just like distributive property. So if I were to do negative 3a, remember capital A, and that means a matrix. So I'm going to do negative 3 times matrix A. And I'm just distributing negative 3 to every entry in the matrix. So then I get negative 6. Negative 3 times negative 3 is positive 9. Negative 3 times 0 is 0. And negative 3 times 7 is negative 21. Okay? It doesn't have to be an integer. It can be a fraction. So you're doing the same thing. So distribute the 1/2 to every entry. Keep your answers as fractions. You're multiplying by a fraction, so keep your answers as fractions. Okay, so 1/2 times 2 is 1. And then negative 3/2, 0, and 7/2. Questions about that? Again, don't overcomplicate this. Don't overcomplicate it. We're going to put together the scalar multiplication and the addition and subtraction. So because we're adding and subtracting, we need to make sure that they're the same size, so you would check that first. So matrix E is what size? And G? Okay, so can we subtract those? Yes. Follow order of operations, so multiply E by 3 first. Okay, so we're going to multiply that by 3. So 3 times 1 is 3. Negative 6, 0. 0. Negative 3, 6. 12. 9, negative 18. And then I'm subtracting G, so I'm just going to copy G down. 1, 2, 0, 0, 1, negative 2, negative 4, negative 3, 6. And then subtract. So make sure you're subtracting each entry. You're starting with the 3e. So 3 minus negative 1, that's 4. Negative 6 minus 2 is 4. 0 minus 0 is 0. 0 minus 0 is 0. I'm right here, so negative 3 minus 1 is negative 4.
Yeah, negative 6 by 2.
Wait. Where am I? Where are you? Oh, negative 8 up here. Thank you. So negative 6 minus 2 is negative 8. Thank you. 6 minus negative 2 is positive 8. 16, 12, 12 minus negative 4 is 16. 9 minus negative 3 is 12. And negative 18 minus 6 is negative 24. Okay? All right, look at the next one. C plus F. So C is what size? 3 by 2. And F is 2 by 3. Are those the exact same size? Nope. So this is not possible. Okay, 4H plus 2A. So H is what size? 2 by 2. And A? Are those the exact same size? Yes. So we did that one. So go ahead. I'll let you finish that one up. Okay, Kyle, what was your final matrix?
36, negative 6, negative 10, 24.
Okay, we agree? Yep, that's correct. All right, questions about that? Okay, again, it should not seem too hard. It should seem pretty simple. We're going to start matrix multiplication, so we'll go over this more tomorrow, and I'll show you tomorrow how to do it on the graphing calculator. So we're just going to get started with it today. So this is when I multiply two matrices together. So it's not as simple as the other stuff that we've been doing. Once you understand the pattern, then it's not that hard, but it is going to be something new. So what this chart tells me is that in order to multiply matrices, they don't have to be the exact same size. What has to be the same is the number of columns in the first matrix has to match the number of rows of the second matrix. Okay? So this is H times A, so this is matrix H, this is matrix A. Matrix H is what size? 2 by 2. Okay? Matrix A is what size? 2 by 2. So I can multiply those because the number of columns is the same as the number of rows of the second one. I don't actually care what the first number is. I don't care about the rows of the first or the columns of the second. Okay? What has to be the same are these inside numbers. So I would recommend writing them next to each other because you'll look at the inside numbers. So those must be equal. What the outside numbers do tell me is what my resulting matrix will be. Okay, so those 2 by 2 will be the sides of your new matrix after you multiply. So when I multiply two matrices together, I'm not just multiplying corresponding entries like I do with addition and subtraction, because they're not always necessarily the exact same size. What I'm doing is the rows of the first one times the columns of the second one. So I know my new matrix will be a 2 by 2. Okay? So I'm going to write out the lines here. So I know I'm going to finish with a 2 by 2 because that was the outside numbers. Alright, so to get my first entry, that's row 1, column 1. Row 1, column 1. So I do the rows of the first one, row 1, columns of the second one. Row 1, column 1. And I match up the first and second entries of those. So I'm going to do 8 times 2 plus negative 3 times 5. Okay. I will do the simplifying here in just a little bit. I want to write out the multiplication first. Okay, the next one I'm going to look at is the one I have underlined here in green. So that's the first row and second column. First row, second column. I'm going to do the same thing. So I'm going to do 8 times 3 plus, so you add in between the multiplications, negative 3 times 8. Now let's look at the blue line. So what position is that? That's row 2, column 1. Okay, so row 2, column 1. So that's negative 5 times 2 plus 2 times 5. Okay. Negative 5 times 2 plus 2 times 5. And then the last one I have will be row 2, column 2. And that's negative 5 times 3 plus 2 times 8. Alright, I would just then simplify these all together. Type them in your calculator if you want all together. But if I write it out, 8 times 2 is 16 plus negative 15. And then I have 24 plus negative 24. And then negative 10 plus 10. And then 15. Negative 15 plus 16. And I end up with 1, 0, 0. That's a special matrix too. You're not always going to end up with that. That is called the multiplicative identity, which with real numbers that's 1. Like 3 times 1 is 3. It's whatever you get to be yourself. With matrices, it's your diagonal of 1s and the other part's 0. So if you multiplied any matrix by this, you would get itself. And that's labeled as I. And we'll talk more about I. at this other one though. Okay. So the size of F is what? 2 by 3. And the size of A is 2 by 2. Remember, it's these numbers that have to be the same. They are not the same, so this is not possible. But what if I switched the order and I did wanted to do AF? Okay. Then I'm doing a 2 by 2 and a 2 by 3. Okay. Now those are the same, and you could multiply. Okay. So multiplication, matrix multiplication, is not commutative, meaning the order matters. Okay, so it's not like with real numbers, if you do 2 times 3, you get the same thing if you do 3 times 2. Okay? Matrices are not that way. The order matters. If you did multiply A times F, then your new matrix would be a 2 by 3 matrix. And we will practice more multiplication. We're going to stop there. We'll practice more multiplication tomorrow.